This is section 10.2 on adding and subtracting rational expressions. This is actually more challenging than multiplying and dividing because you have to work a little harder to add or subtract, which sounds counterintuitive, but you'll see what I mean. So rational expressions are fractions, so we always have to keep that in mind. In order to add or subtract them, we must have what we call common denominators, and we saw this back in chapter 2 when we were trying to solve with fractions. Anytime you're trying to add or subtract any sort of fractions, you have to have common denominators. If you already have common denominators, you just add or subtract the tops and simplify. Remember, if you're adding fractions, like if I have 2/5 plus 1/5, if the denominators are the same, we just add the numerators and we leave the denominator the same. So it becomes 3/5. So kind of keep that same idea in mind for these. So example 1, if I have x over 4 plus 5x over 4, they're both over 4, so I can just do x plus 5x all over 4. This is like 1x plus 5x, just 6x over 4. And then we can simplify from there. Divide them both by 2. That would be 3x over 2 for our final answer. Same idea on example 2. X squared over x plus 7 minus 49 over x plus 7. So the denominators are both x plus 7. So we have x squared minus 49 put together over that common denominator, x plus 7. And factoring always sneaks into these, so this here is a difference of squares, so it's going to be x plus 7, x minus 7, over the common denominator, x plus 7. And just like we saw with simplifying, if we have matching binomials, we can cancel them out for a final answer of x minus 7 over 1, or we can just leave that simply x minus 7. So sometimes there's a little bit more you can do depending on what happens when you put things together. Let's look at one more with common denominators. We have x over 3y squared minus x plus 1 over 3y squared. Anytime you see a binomial in a rational expression, I always recommend parentheses so you can keep it together. So it's going to be x minus parentheses x plus 1 all over 3y squared. We'll distribute that subtraction to the entire binomial. So x minus 1 over 3y squared. X minus x is 0 x's, so we just get negative 1 over 3y squared. So you're left with an expression that might be a little more simplified or more complicated, just depending on what you're working with. But that's the basics. If you already have common denominators, you just add or subtract the tops and simplify as appropriate. When the denominators do not match, we must make them match by using the process of making common denominators, which sometimes involves factoring first. So let's think about plain old fractions here for a second. If I had 2/3 plus 1/4. Cannot see that. If I had 2/3 plus 1/4, the 3 and the 4 I'd have to make common by multiplying this one by a number and this one by a different number to make them match. That would give me 8 over 12 plus 3 over 12. So your final answer would be 11 over 12. So just keep that in mind. We have to multiply the top and the bottom by some number, depending on what you're looking at. It could be any number, to make those denominators match, and then we can add them together. So keep that little process in mind as we go through these. These build in difficulty. I'll keep watch of the time. I'll try to keep my videos around 20 to 25 minutes. So I might pause in the middle just to give you guys a break, and then I'll start recording again to continue with the examples. You might want some colored pencils for this. 2 or 3 different colors can be helpful. Make sure they're distinctly different. It's hard to see in the video. I have green, red, and blue. So something distinct so you can really see. Colored pencils are always helpful in helping you take proper notes. So let's look at example 4. We have 2 over x squared y plus 5 over 3x to the third y. So we have to inspect the denominators. They both have y. This one has x squared and this one has x cubed. This one has a 3 and this one does not. So with a different color, something bold so you can really see it, we're going to have to multiply this first fraction by something, whatever it takes, to make it match the second fraction. So definitely going to need a 3 on there. And whenever we multiply the bottom, we have to multiply the top. And we're also missing an x, so I'm going to have to also multiply by x. If I multiply this denominator by 3x, it will now match this one. So this is a thinking process. It's not always obvious what to multiply by, but you have to multiply by whatever it takes to make those denominators match. From there, we'll clean up what we have. So 3x times 2 is 6x. Over, multiplying this together, we'll get 3x to the third y plus 5 over 3x to the third y. Now that the denominators match, we can put the tops together, and we'll get 6x plus 5 over 3x to the third y. Remember, 6x plus 5 becomes a binomial, so we can't separate that, and that will be our final answer. If you'd like to try the next one on your own, it's extremely similar. You can pause the video, try it on your own, and see how you do. Again, we kind of inspect what we have here on the denominators. They both have q. This one has p to the third, this one has p to the fourth. This one has a 5 and this one does not. And so you notice I gave you some more space on the side for these. You always want to give yourself what I call side to side or elbow room for these problems, because you're going to be multiplying on from the side. So they definitely both need a 5, top and bottom, and we're missing one variable p. So just multiply the top and the bottom by the same thing. Then we will clean that up. So 5p times 4 is 20p. Multiplying these together, we should get 5p to the fourth q plus 3 over the same denominator, which should be a q. So that's going to give us 20p plus 3 for the top over 5p to the fourth q. And you can put parentheses around that because it becomes its own binomial. So our answers again are going to look a little funny. We will solve these eventually and it makes it easier to see, but right now your answers are just kind of expressions. Let's look at example 6. We have x plus 2 on one denominator and x minus 2 on the other. Those are two distinct binomials. So the first fraction, the first fraction, we'll get x minus 2. And you might want to do this part in a different color. The second fraction, we'll get x plus 2. And notice I put parentheses around the whole thing, so whatever we do to the bottom, we have to do to the top. So if you look now, there's x plus 2 on both fractions, and there's x minus 2 on both fractions. We leave those denominators just like that. We do not have to multiply them together or anything. We do need to distribute since it was a binomial here and here, and then we'll see what we have. So multiplying that out, we get 3x minus 6 over x minus 2, x plus 2, plus, we're going to do this over here, 2x squared plus 4x over that same denominator, x minus 2, x plus 2. From here, all the numerators can come together. So I'm going to put the 3x plus the 4x. I'm going to put the 2x up front and the minus 6 at the end. So hopefully you can follow all that. I'm going to start with 2x squared. 3x plus 4x is 7x, and then the minus 6. Hopefully that wasn't too much at once. So all together, combine like terms on top, leave the denominators as binomials, x plus 2, x minus 2. So you clean up the numerator using the operator that you're given, and you leave the denominator alone. And it doesn't matter if you have x plus 2 or x minus 2 first, as long as they're both on there in either order. Let's look at one similar to that. Again, you can pause the video if you'd like to try them on your own. Let's see here, example 7. We have y plus 3 and then y minus 3. So using distinct colors, I'm going to multiply that first fraction by y minus 3, because that's what it's missing. And then I'm going to multiply the second fraction by y plus 3, because that's what it's missing. And it looks a little messy right now. We're going to go ahead and distribute the tops, and then we'll clean them up. That gives us 4y minus 12 plus 5y squared plus 15y, and that plus in the middle should really be here. And they're both over y minus 3, y plus 3, which you can write separately at first, but we're going to bring them together anyway, so you can just write it together from the beginning if you want. Again, I'm going to put the squared term up front. They're just being added, so it's nice and simple. I'm going to put the constant on the back, and I'm going to combine my like terms here and here with addition. So that will give me 5y squared plus 19y minus 12 altogether over that common denominator y minus 3, y plus 3. And that's how your final answer looks. You don't have to multiply those back together. Example 8 looks a little tricky here. First thing to notice, you've got subtraction in the middle. You have to be really careful when you have subtraction in the middle. You have x minus 1 over here and 1 minus x over there, so it's a little tricky. I'm going to switch the order and make that negative x plus 1 like we did in the previous section. And then I'm going to take out that negative 1 so that it now matches that guy. So what I have here is 2x minus 6 over x minus 1 minus, from the original problem, 4 over negative 1 times x minus 1. The minus from the problem and the negative 1 I took out come together to make a positive. So I'm going to have 2x minus 6 plus 4 over x minus 1. So to be very careful, write that very carefully. That negative 1 combines or adds or subtracts, or however you want to think about that, with this subtraction in the problem. So it becomes a positive. So then I can put the negative 6 with the positive 4 for a final answer of 2x minus 2 over x minus 1. One last thing to notice about this one is that this has a GCF. I can take out a 2. That leaves me with x minus 1 over x minus 1. And anytime you can see that, anytime there's a GCF, something to factor, something to take out or simplify, always do that. So we can divide those guys off for a final answer of just 2. So that's a tricky one. It looks easier than it is. It has a lot of little steps in it, so you really have to, one step at a time, see what you can do. Just don't try to jump ahead or skip steps. Do one step at a time. I strongly encourage you to pause the video and try example 9. It's very similar to example 8. Try that on your own and see how you do. Just like example 8, this 5 minus z is where I'm going to focus first. I'm going to switch the order and take out a negative 1. So what that's going to do, especially with that subtraction, don't want to miss that. A lot of students will just change it to addition. Don't change the problem. Keep it as it is. It was subtraction. I took out that negative 1. So again, that negative 1 and the minus kind of cancel each other out to become addition. So we're going to have 3z minus 18. It's going to become plus 3 over z minus 5. Then I can put the minus 18 with the positive 3. That's going to give me 3z minus 15 over z minus 5. Take out the GCF on top of 3. Always scan for those. That's true anytime you have polynomials. Those will divide off for a final answer of 3. So each one works out very differently. It's hard to see at the very beginning where it's going to go. You just kind of have to follow it along one step at a time. Let's keep going, moving on to example 10 and 11. Looking at example 10, I always look at the denominators. We have x minus 1. We have x squared minus 1. X squared minus 1 is a difference of squares that factors into x plus 1, x minus 1. That's something that's hard to catch sometimes. Your eyes just don't see it all the time, especially if it's a 1. You have to remember that 1's a perfect square, and the difference of squares does factor. So what I have, and I'm going to give myself some elbow room here, 7 over x minus 1. I gave myself some space here, plus 10x over x plus 1, x minus 1. So always factor if you can. And it's easier to see what's missing. So they both have x minus 1, but the first expression needs x plus 1. So we're going to multiply on x plus 1, and that way they both have x plus 1 and they both have x minus 1. Then we'll distribute there. That's going to give us, I'm going to write it down here, 7x plus 7. The original problem was addition, so plus 10x all over that common denominator, x plus 1, x minus 1. So you can put all the tops together, just watch your sign, and then over that common denominator. And then we just clean up the top. So final answer would be 17x plus 7, putting the 10x and the 7x together, over that same denominator, x plus 1, x minus 1. And that would be your final answer. Example 11 works the same way if you want to pause the video and try it. They always the examples come in pairs in the textbook, so it's always good to pause and try the second one on your own. Just see how you do, and then play the video back. So looking at the denominators, we have x minus 2, x squared minus x minus 2. Let's see if we can get that factored. The giveaway is the squared. Anytime you see a squared, you have to factor. So if you want to highlight that or circle that or whatever you want to emphasize, if it's squared, you have to factor. Anytime you see a squared on the denominator, you've got to factor somehow, some way. It might just be GCF, but you've got to factor. So this factors into x plus 1 and x minus 2. So what we have is, I'm going to give myself some space here, 2 over x minus 2 plus 3x over, and I'm going to put it in factored form, x plus 1, x minus 2. And then colored pencils come in handy. They both have x minus 2, but the first one is missing x plus 1. So we're going to have to multiply on x plus 1. And I try to keep the numbers small for these because it's enough work already, so just know that it shouldn't be too complicated. Then we're going to distribute that 2, and we'll combine the tops. So you should get 2x plus 2 plus 3x, putting all the numerators together, over the common denominator, x plus 1, x minus 2. That's going to give us a final answer of 5x plus 2 over x plus 1, x minus 2. And I'm going to pause there, and I'll record those last few examples in a separate video.